All right, so for today's lesson, we're going to focus on thinking about the groundwater flow equation in a transient system. And then we're going to think a little bit about this idea of the differences in what's called storativity in confined and unconfined aquifers. So let's get started. So we've seen this equation before, right? We've seen that if we think about a heterogeneous system and an anisotropic environment, right, in 3 dimensions, we could represent the equation, the groundwater flow equation, like this. And then before we've said, okay, we're at a steady state condition, and so therefore it has been equal to 0. But now what we're going to do is we're going to actually say that it's equal to some change in the specific storage of the system as we have a change in head over time, right? So that's what we're going to be considering now. So by making this or bringing this system as a component of time and a component of a change in that specific storage of the system and the head of the system, we have now created a transient environment. So let's go over some terms that you're going to need. And it's important to kind of get these written down correctly because you can kind of get confused with the number of S's that are about to come up. So just writing them down and underscoring what they are is important. So go ahead and pull out your equation sheet so we can get this started. So our storativity is the volume of water per unit area head change. So how much water is given up in a given area when we change the head, right? And that could be the change of the head in an increasing way or a decreasing way, right? Volume of water would be in units of length cubed, right? It's a volume. And an area times some depth is also a volume. And so therefore, essentially, it is unitless. Another way to write this equation is to say that our storativity here is equal to our change in storage divided by our area multiplied by our change in head. Specific storage is slightly different. Specific storage is the volume of water again. So again, we have that change in storage on the top, but now we've added a new term. So it's per unit area, per unit thickness of aquifer. So that B term that we've used, right? So that in itself is a volume now per unit head change. So essentially now we're left with 1 over a meter, right? Because we have meters cubed on the top and meters to the 4th on the bottom. So the specific storage value that we see here, right, is equal to our change in storage divided by our area of interest that we're looking at, multiplied by our thickness times our change in head or change in unit head. So we can say that we can relate our storativity here, the big S, to our specific storage here by multiplying by the thickness of our aquifer, B. So we could also reduce, again, we could rewrite this statement just to say that our specific storage is equal to our storativity over our thickness. So why are we going through all of these terms and why are we considering these different environments? One thing we have to consider is the volume of water that's given up, whether or not you are working with a confined or an unconfined system. So on the left-hand side, we have our confined, on the right-hand side, we have our confined aquifer. On the left-hand side, we have our unconfined aquifer. And for an equal drop in head, right, or an equal change in pressure over here, we could think of that as a change in our pressure of these systems or our total head. We have different volumes of water that are released. And so this is our storativity term, the volume of water, right, per unit area, per unit head drop, storativity. So when we come back to this, when we think about our equation, we can write our groundwater flow equation, this one being in 3 dimensions on the top, thinking about that specific storage here. Or if we take into consideration the thickness of our aquifer, we could say it's the storativity, right, of our system over a change in head, over a change in time. And instead of using K, which is our hydraulic conductivity, right, in different dimensions, now we're moving back to isotropic and homogeneous, we can add in that thickness term and we can turn it to our transmissivity. So remember, transmissivity just equals our hydraulic conductivity times our aquifer thickness. So we're just going to say that it's equal to our T equals K E. So essentially multiplying each of these by a B. So there are three mechanisms that we think of when we think about head drops in a system. So the three mechanisms are caused by the fact that water expands, but this only gives up a small proportion of water. We also have the fact that pores contract. So we have the fact that water expands, and we have the fact that pores contract. That also gives up a small volume of water. And then we have something where the pores physically drain. And we've kind of talked about this already in unconfined systems when thinking about specific yield. So in a unconfined aquifer, right, because we can have drainage that takes place, our storativity is very large. But in unconfined aquifer, in confined aquifers, right, on the right-hand side, we don't drain that system when we have a unit head drop. We're instead giving up, we're allowing water to expand, we're allowing pores to contract. And so the amount of storativity, the amount of volume of water given up is actually quite small. So in unconfined aquifers, all three mechanisms are at work. Drainage of pores is very important and usually accounts for almost all of the water being released. Not 100%, but really, really close. Storativity is usually between 0.1 and 0.25. And it's approximately equal to your porosity of your system. So sometimes we have to make some assumptions, right, about our environments. And here, this might be an assumption that you're asked to use in the field when starting to make a back of the envelope calculation. Confined aquifers do not have a drainage of pores, even though you can have a unit change in head. So that unit change in head, remember, we've always been talking about it in this idea that there's this overall pressure being felt at the system, this total head. So you can have this change, but the storativity usually is about 10 to the minus fifth to the 10 to the minus third. We oftentimes in confined systems talk about another term, which is that idea of the specific storage. So specific storage, again, we've already gone over this, is that change in storage that we have over our area, over our unit, our aquifer thickness, multiplied again by that change in head drop, or it's our storativity divided by our thickness. So let's go ahead and think about some storativity details. For a confined aquifer, remember, expansion and compression are what can change water levels and what can allow for water to be given up in a system. So if we think about our specific storage here, we can think about it as being properties of this expansion and the compression. So let's walk through these. So we have our density of our water, we have gravity, then we have our porosity, that's in here, and then we have the vertical compressibility of rock, that's going to be here, and the compressibility of water. So again, in a confined system, we're thinking about the density of water, right? It's giving us some idea of the system, gravity, the amount of pore space that we have, and then the compressibility of the rock and the compressibility of the water. In unconfined systems, the majority of the water is as a result of gravity drainage, right? So we have our storativity yield, which is equal to our specific yield, plus our thickness times our specific storage. Our specific yield is the volume drained to the total volume of the system. And remember, we've already made these calculations before earlier, and our specific yield, right, can be somewhere between 0.1 and 0.3. And our specific storage values here are going to be 10 to the minus third to 10 to the minus fifth. So if we go back, we can begin to think about, right, when we start to say, okay, what is our specific storage in our system? We can multiply that by our thickness, and we can begin to bring in this idea of a transient groundwater system. So, just to go over and think about it, what these equations really mean is that in 3 dimensions, we are thinking about how the flux, and we can think about that as the volumetric flux, right, Q, or the specific flux that we have, Q, how that flux in the X direction must be balanced by changes in a flux in the Y direction and a flux in the Z direction, as well as some change in storage. So mass is still balanced, right? We have our inputs minus our outputs, which are now equal to a change in storage. And this goes back to kind of the very first lectures that we had. So H can be calculated everywhere and over time, only knowing just a couple of things. So if we think about this again in 2 dimensions, this idea of just a couple of things is head at some position in the X and some positions in the Y direction, as well as some knowledge of the aquifer properties here, transmissivity, and some knowledge of the change at which head has occurred over some change in area per unit head drop, and how this is occurring over time. So it relates changes in head over time to changes in space by properly accounting for Darcy's law and mass balance. So we can think of it as we can find the head levels, right, as a function of the X and Y direction, right? That's what that function term means down here, over time. And so if we're solving this function, if we're solving this equation, and we can determine what head is in any position, we call this solving the groundwater flow equation. Now, I want to give you a reason for, why we are really interested in being able to think about changes in storativity, changes in what's happening in aquifers, and how those changes are occurring over time, because it has implications for the available water we have for pumping. So here we're going to take the case study from the Chicago area. And so this is looking at water levels pre-development in the Chicago area, okay? So you can see this is feet above mean sea level, pre-development, this is head. So these are those contours or potentiometric surfaces that we've looked at of water level, right? Going from the highest water level, if we were flow, down to the lowest water level, potentially here, or ending up down in this region. So when we take a look at this system, there's a series of confined aquifers. They're confined by a shale system. We have Lake Michigan, that's over in this environment here. And our head levels would have led to a system where our general groundwater flow paths would have been what we see here. Now, over time, right, 50 to 60 years into the future, we've begun to pump, and we've seen that we've had some changes in the water level, right? So this is the overall head level that we have. We see a change in that head level as a result of the beginning of pumping in this environment. And then by 1975, again, here, city of Chicago growing to a greater extent, more wells put into the system for it. And we see an even greater head drop in this confined system, right? Using 46 million gallons of water being pulled in per day. So what does that do to the hydraulic head? So since we've had our development, our drawdown has changed, right? So here's our water level. Here is going to be, this is the proportion of drawdown. So less than 100 means very little drawdown is being impacted. And as you move to higher numbers in this system, right, that's a greater degree of drawdown. So it's kind of an inverse to a potentiometric surface map. Okay, so this is drawdown since pre-development. And so we can see how much has been drawn down in this environment. We've had drawdown of almost 800 to 900 feet in this area around Chicago. So if we take kind of present day conditions and we can see these different aquifers that are within these different kind of shale formations, there is some degree of connection between these environments because of the faulting that's taken place in here. So that's important to also take into consideration. We see the pumping that's taking here and the partial actual desaturation as a result of the strong degree of pumping. And then we can see what happens as we continue to pump in these environments. You know, about, just 30 years into the future, what will start to take place. And we see that this pumping in these environments is actually causing a greater degree of drawdown such that we're actually impacting the water flows in the aquifers, in these confined aquifers that are even below as a result of the fracture units that connect these unconfined or these confined systems.